Okay, just as I said, I posted the entire homework set for chapter 2 on Moodle, okay, in the same place as the first set of homework of chapter 2. I just extended, okay, the homework set. Now total like 13 problems here. So maybe the last couple problems you still don't know how to do, haven't finished chapter 2 yet. Okay, I still have a couple section left. But it's okay, I posted it in advance. Okay, so that's all of the chapter 2 problems. Okay. Okay, let's have a little review so far for the thing subject. Okay, oh, by the way, video project will be due next Monday for the first half of the chapter 2 content, right? First half. So then will be next project will be the second half, would be from the heat source and the things. Okay, so it will be again will be due 2 weeks later. So not 2 weeks from today, from 2 weeks from next Monday, I guess. I always give you 2 weeks to doing those experiments. Okay, I started to grade your first video. Okay, I graded several of you. Some of you already see the grading there. I put down the detailed grading for each category. They're I show in the description, right? There are the 4, 5, 6 categories. I put down the detailed grading for each categories. Okay, so take a look. Let me know if you have questions. I didn't finish it yet, but I started. Some of you already see the grade, some of you don't. It's okay. Just be patient and wait. By the end of this week, probably most of you will see the grade. Okay. I'm probably not gonna grade too much today and tomorrow. I will be back in Lake Charles for a trip. So I'm on the road and I probably don't have the computer to see that. And I probably will start to grade more Friday, Saturday. So by the weekend, most of you should see the grade for that first video. Okay. The second video will be due next Monday. Okay, so the third video will be the rest part of the chapter 2. Okay. Okay, now let me share my screen. Okay, we spent a couple classes on the thing. So thing, let's review it, right? Thing, you have case 1, case 2, case 3. Each different type of boundary condition, you have solutions. Temperature solution, theta over theta 0, it's a temperature solution, okay, as you know. Theta equals to the reference temperature, right? T minus T wall, okay, that's theta. So theta 0 is T0 minus T wall, okay? T0 means the base temperature at the thing, okay? It's so each case you have a temperature equation, then you have a total heat transfer equation, total heat lost by the thing, okay? Your adding thing is, the purpose is to lose heat, right? So the bigger the Q is, the better your thing is, okay? So that's the case 1, case 2. So equation, the solutions are long, so you might not be able to memorize all of them, but some of them you probably be able to memorize, right? Okay, so also case 3. We also mentioned case 1 is not that often. It's infinitely long things. You usually in practical industry application, you don't see infinitely long things. So between case 2 and case 3, many times we can use case 3 to represent the solution. Case 3 is a finite length of thing, but with the insulated boundary condition. Phase 2 is a finite length with convection heat transfer boundary condition at the tip. Okay, so if the thing is long, it's not very short. If it's long, then the heat transfer through the tip is minimal. So in that sense, you can approximately assume that heat transfer at the tip is negligible. Basically, it will be equivalent to the insulated boundary condition. So the case 3 is the most often used case. Okay, also have temperature and the Q. Look at that. Notice there's a letter M the expression for m. Okay, so here are the solutions. Okay, that's then we talk about the thing efficiency last time, right? Thing efficiency, we provide, that's a definition for thing efficiency, actual heat transfer divided by the ideal heat transfer if the surface temperature of thing on the entire thing is the same and it is in the equal to the base temperature, which is the ideal case, the maximum heat transfer case. Okay, so efficiency is defined like that. Okay, so we only provide the efficiency for the case 3. Okay, case 3. And with some, this is the initial equation, right? With some assumption, you can we assume the thickness of the thing is much smaller than the depth of the thing. Okay, by the way, here I want to emphasize, listen carefully, emphasize the 3 dimensions we use in the thing. Please be clear what we call it. Okay, thickness, always, you know what thickness means, right? The thickness of the thing. And the Z, which means is the depth of the thing, which is going into the paper, from the drawing. Okay, length is actually the length of the thing. Okay, thickness and the length is what you use it to define the profile area. Okay, frontal area of the thing, and the depth is Z. Okay, so length, depth, and the thickness. Okay, so for the ML calculation in the efficiency as well as in other in the Q and in the temperature, if there's ML, it can be simplified into this form: ML equal to this, as well as this if we want to use the profile area, L times T to represent. So that's how you calculate the efficiency of case 3. Okay, with the assumption the thickness is very smaller comparing to the depths. Okay, it becomes these 2 formula for ML in order to calculate the efficiency. Okay. For case 2, we try to use the same equation as the case 3. Okay, replaced by the corrected length. Okay, the correct length is defined by this for the straight thing, and there's another expression 2.42 for the cylindrical things. Okay, so circumferential things. So we'll look at the example later about that. But here, case 2, basically we can use exactly the equation for this efficiency equation as case 3 with the corrected length, L plus half of the thickness of the thing. Okay, so with a condition of this, very important, listen carefully, this is the condition you want to check, not only just for calculating efficiency, but also for calculating heat transfer, total heat transfer loss, as well as the temperature. You can always use case 3 to replace case 2 if this condition satisfied. Square root of HT divided by 2K. If it's lower, less than 0.5, half, then it's safe to apply case 3 equation for case 2 problems. Okay, can you remember this? Very important. So this is the check. Okay, if this condition is satisfied, what do I mean by safe to use case 3 equation for case 2? Safe means the error will be less than 8%. Okay, so it is okay. Okay, so this is what we have so far on the theory part. Now let me give you a equation. But give me an example before we continue on other thing contents. Okay. The example is example 2.9. Any question before I move on?
Whenever you're talking about the thickness and the depth, I couldn't really quite picture. I mean, I'm sure.
Do you have can you open up the group me? Okay. Did I send you the picture of that? Group me to our class?
Yes, sir.
Okay. Please look at that picture. Understand the picture here. The dimension, the thickness. Do you know what the thickness means?
Yeah,
the thickness. A mark down there. Okay. How then? The length is obviously L. That's the length of the thing, right? Do you know
And the Z is how far back it goes.
That's called depths. Here we call it the depths. Okay, in the whole entire textbook we call it depths. So
Alright.
please be understand. Yeah, what's the convention? What's the name you use? Okay.
Yeah, I was just making sure.
Yeah, good. Okay, example 2.9 look like this. An aluminum fin. Okay, so the K is given. K is 200. The fin is aluminum, meter per watt meter C. Okay, the thickness T is 3 millimeter. Wow, it's pretty tiny, huh? 0.003 meter. Okay, the length of the thing is 7.5 centimeter. Okay, protrudes from a wall. Okay, as shown in 2.9. Just the 2.9 figure 2.9 is the figure I posted in group me. Okay, that's just basic geometry. The base is maintained at temperature 300 degrees. T0, we use it as the base temperature, 300 degrees C. Okay. And the ambient temperature, T infinite. Notice this is not T wall, okay, it's T infinite, okay. It's the ambient temperature. Seems like it is convection, huh? The tip, okay. With the heat transfer coefficient H of the air is 10 W over meter square C, okay? Calculate the heat loss from the thing per unit depth of the material. Per unit depth, that means the depth unit means 1 meter, okay? Basically it's 1. Okay, so calculate the heat loss. Okay, what equation we're gonna use? Okay, I really like you guys.
Probably your Q equation.
Which equation? You have how many equations? You have 3, right?
I got 3 of them.
So which case you're gonna use? So look at each case. I really want you to remember all the 3 cases. What are the 3 cases? I said it a many times, right? What is the first case?
Super long.
Super long. Is it super long? Infinitely
super
long. This is not super long, right? It's still finite, right? Although it's much longer than the depths. I'm sorry, the thickness, right? The length is longer. Okay, so between 2 and 3, actually, which case is this?
I believe it's 2.
Okay, it seems like it's 2. Okay, can we use 3? That's always the question you ask yourself if you see a problem. Can we use 3?
It depends if that thing is less than 1/2, right?
Okay, so I leave it for later. Okay, let's look at the solution on the book first to see what the book says. He didn't say anything basically on that solution, that's why you need me, right, to explain to you. He picked 2. He picked 3. Look at the equation here. He picked the Q. So if Q equal to, right, Q is what we want to find out. Q equals, it says TANH hyperbolic tangent MLC. Okay, notice he already put the LC there, right? Square root of H P K A and times theta 0. Look at your notes. Look at your notes. Is it, double check, is this equation for case 3?
Sure is.
Yeah, it is. Okay, he didn't say anything, but obviously this, to me, when you read this problem, if you haven't taken this class, you know some equation for thing. Okay, obviously this should be the case 2, but he actually, the author actually presented case 3. Okay, but that's all right. Let's keep doing it. Case 3. Let's calculate first. Let's then extend the discussion. Okay, so in order to calculate this, what do you need? I need most of the stuff in here, right? I don't have most of the stuff, I think. Okay, so Do we have anything? Oh, okay, I think I have some. Okay.
We have H and a K.
Okay, I think we can. Okay, hold on. Let me admit a student. I have an alternate equation in my lecture. I showed you. Okay, m. That's also we can use m k a theta 0. Okay, theta 0 times TANH ML. MLC, nothing you can do, right? Okay, so this term is equivalent to this term, right? We wrote it down on the notes. Okay, this is alternate equation. We just make some mathematical trick. So make it to, so either this or this you can use. I think this one is easier. You don't have to have that square root. Okay. Okay. So I think that's what the book use, right? Yeah, let me double check. Okay, so that's what the book use. So this equation. So what do we have? We have k, right? Definitely. Okay, that's not a problem. K. Okay, it's 200, right? 200. Do we have the? I always like to start from simple. Do I have the area, cross-sectional area of the thing?
Well, we're doing it per. What does it say? It says. Oh shoot, I lost it.
So what this
We're doing
letter?
it per unit depth, so we don't. It's
I
just
already said it. The depth C is 1 meter, unit
right.
depth. So it's safe to put it as 1 meter. Basically, you don't even need to put the unit there, just one. Okay. So what is the area?
The thickness.
Thickness times 1. Okay. So it's 0.003. Okay. So both K and A is there. Okay. LC. I see an LC here. Okay. K is given. Now the calculation for those thing problem is tedious, right? Be careful, don't make mistake. That's what I try to do now here. I write it down each terms I have. A is 0.003 times 1 meter square, okay? And LC, okay, LC we have the equation, right? Do we have that equation, LC? What is LC? Just for the straight thing. Remember? Corrected area, or corrected length. It's the length adding the tip length, right? Half of the tip thickness. Half T. Sorry. Right? Is that the equation we use? Okay, so LC should be there. It should be 0.075 plus half of the 3 millimeter, right? So it will become very small, okay? 0.0765 meter. I really like to convert everything into the meter. Look at the book. He keep using centimeter or something like that. I don't like it. Use the meter. It's straightforward for your calculation. What's left?
What is that next to the L? That's LT what?
LC, corrected length. And that equals to L plus half of T, half of the thickness. Okay, we're going through here. This is really not difficult. We just go through here, try to memorize. Hey, I always want you to guys to memorize the equation. Okay, you always feel, why do I need to memorize it? I have a textbook. I can always read the textbook. I can read online. I can find the equation. Memorize the equation if you can. Then it can speed up your process of solving problem, and you can make you less frustrated. Okay, during a complicated problem solving process. Okay, that's why I try to memorize more equation if I can. Okay, sometimes if too much, then I cannot remember. But some of the equation, like corrected length, it's really not difficult. It's L plus the half of the thickness. Just like you fold the tip straight. Okay, extend it to the length, then become half of the thickness. Okay, something like that. Okay, what else? Theta 0. Okay, theta 0 is, he made a assumption that at the tip, it's case 3 now. So the heat transfer through the tip to the surrounding is negligible. If it's 0 heat transfer from the tip and surrounding, we can assume the wall temperature at the fin tip is the same as the ambient temperature, okay? You know what theta 0 is? It's a reference temperature. It's temperature, it's 0 minus temperature at wall. Okay, in this problem, it didn't provide the wall temperature. Okay, it gave you the ambient temperature. But here, we assume the ambient temperature is equals to the wall temperature with the assumption it's case 3. Okay, it didn't say anything about why it's case 3. Okay, but it's case 3. Okay, since it's case 3, the tip convection heat transfer is 0. Then if the convection heat transfer is 0, the temperature on the wall has to be 0 because otherwise H is not 0, A is not 0, so HA delta T, right? Delta T has to be 0, so T wall has to be T infinite. So based on that, it will be 250 degrees C. Okay, we got this. We get everything, right? Except what? Except M. Can I use the next page? I'm out of, okay. Look at this equation. We know everything, right? Everything except M, right? That's why I'm going to write M in the next page, okay? Any questions so far before I move on to the next page?
Why is theta 250?
Theta equals to T0 minus T wall. Do you agree, this equation?
Yes,
This is
sir.
the definition, okay? What is T0 in this case?
It is 300 degrees Celsius.
Okay, what is T wall here?
We don't have it.
We don't have it. That's my discussion. My previous 3 minutes discussion is about, we assume because it's case 3, it's a insulated condition at the tip, and the convection from the tip to the surrounding is 0, is negligible. We assume it's 0, 0 convection heat transfer. From the tip is a wall, TW is the tip temperature, okay? Oh, first of all, do you understand that TW is the fin tip temperature?
Yes, sir.
Okay, so if from the tip to the surrounding air, there's 0 heat transfer, what does that mean? Heat transfer is 0 equals HA TW minus T infinite. Is that right?
Yes, sir.
Okay, if it's 0, H is not 0, A is not 0, so what must be 0?
The T,
So HA times TW minus T infinite equals 0.
so TW is 0.
No, TW minus T infinite has to be 0.
Okay.
Is that correct? I can write it here. HA TW minus T infinite equals to 0 if we assume there's no heat transfer from the tip to the surrounding. Okay, then look at this equation. H is not 0, A is not 0, so which term has to be 0?
TW minus T infinite,
Okay, what makes TW minus T infinite equal to 0?
if they're the same.
That's right. So that's why TW is 50 degrees Celsius.
Okay.
Okay, good. I want to make sure everybody fully understand this before sometimes I go fast, sometimes I go slow. But if I go too fast, let me know. I want everybody fully understand before I continue. Any other questions? Is that clear to everybody? Okay. Then the last thing is M. M, you have a equation HP. So see, you have so many equations now, right? In heat transfer class, is you have to know the equations. You don't need to know the derivation of the equation, but you have to. But here, HK, we have it, A, we have it. What is P?
The perimeter.
Okay, what is the expression for the perimeter?
C
Was
squared
it
plus Z squared.
No, perimeter.
2Z plus 2T?
That's right. What is the area? Cross-sectional area. T times Z. Right? Is that right? Again, everybody know how to calculate those geometry areas, parameters. These are important, right? This is out of scope of my teaching here, but you're supposed to know, okay? Right, everybody? Cross-section area is the depth Z times the thickness, right? Okay, doesn't matter. I think the book says Z is much greater than T. Okay, so you can just basically neglect that term. So this Z can cancel by the Z. Then the calculation will be more easier, become like this. But it doesn't matter to me. You can just keep the original because we have T and Z. Okay, so the result won't be different. Indeed, the T, 2T can be neglected. It's too small. But that's what the engineer do sometimes. In the field engineer, we want to simplify the calculation. Okay, we don't want to make a mistake, right? If the calculation too long, then it's possible to make a mistake. So it says this, because T is much, much smaller than Z, T can be neglected, 2T here, too small. And then they become H2Z divided by KTZ, okay? Then the Z can be canceled, then become this. Then based on this, you can calculate M equals to what? 5.774. If you still keep the original form, 2Z plus 2T, doesn't matter. It will give you 5.775. Okay, is that no difference? Is that clear? Okay, so that's why this explanation on in the textbook on this one is sometimes it's confusing here. Okay, so with this, do I have everything here? Do I have everything on the right hand side? I do, right? Everything. So we calculate everything clearly. Okay, see, I like you follow the way I do, right? Every letters, I put it in a separate line, equation or the value, whatever I have, one by one, I list it down there. Okay, so even I don't calculate the final Q, I get maybe 18 out of 20. Okay, everything here is correct. That's it. Okay, you have the steps, you have the partial points for the problem. Okay, to finding the final solution is just a little bit of the, so it will be 359 watt per meter, right? You don't have to write per meter. Just let's assume that the depth is 1 meter. Okay. Okay, is that good? Okay. Everybody, any question before I continue? Are you comfortable with this process? Okay, here I have two equations here. I think it doesn't matter which equation you use, it's the same. Okay, it's just a different form, different format of the same equation. Okay, we derived it last time in the class. If you go back to the notes, they are the same. You can still use the first equation. It will give you exactly the same. You just need H, P, K, N, A. Basically, you know everything. Q is theta 0, theta 0 here the same. The tangent tan H, tangent H, hyperbolic tangent are the same, MLC. So these are the two same equations. Don't worry about it. Either one you can use. Okay. Then basically every letters carefully calculate. Very tedious now, right? The kind of calculation, you know. Okay. Any more questions on this?
I kind of have a general question.
Yes.
It wasn't about this problem. And why is 8% the acceptable error? Like, where does that come from?
Well, this is, you know, this is from industry standpoint. Basically, less than 10% sometimes is acceptable. Okay, 8% is the value less than 10%. So I guess that's what we conventionally determine.
It just seems kind of
In industry, you look at the industry application. If you're working to the industry at the internship or whatever, you will see many places you don't have the perfect accuracy in most of the application. You have 1%, 2%, 5% error everywhere. So in an integrated system, if you have less than 10% error, people feel it's okay to proceed. Okay. So I guess here 8% is for something they put a little bit of cushion there, less than 10.
Okay, and the other thing.
Oh, it's not like that. Actually, let me explain one more. Actually, it's based on the calculation. If you use this criteria, use this corrected lens, they calculated using the correct lens and compare with the measured value and the true value. They found that there's 8% differences. Okay, so that's what it is. Okay.
Okay, that makes sense.
Yeah,
And now we only.
I think that 8% is the maximum. Usually it should be less than 8%. Okay, so they put 8% here. Then the 8% should be okay for engineering to make a decision to choose this method, because we okay with 10% sometimes. Okay. Yeah.
And we only use the corrected length when we're able to take a case 2 and use a case 3 equation.
That's
Is that
exactly
correct?
That's correct.
Okay.
If you want to go with case 3, but actually your case is case 2, then you use corrected lens.
Okay.
Okay.
Thank you.
You're welcome. That's really a good question. That's LC is what we use for try to force to use case 3 equations because it's simple. Okay. So that's the goal. Okay. Now listen carefully. I want you to do 2 things as our quiz today. 2 things. I just want you to verify it's okay to use case 3 for this problem. You have that equation, right? Everybody have that equation, right? So I want you to actually calculate the value to see if it's in the satisfactory range. Okay, that's the first thing I'm gonna write down here. On your paper, very easy, do a calculation. Calculate to verify that case it's okay. It's safe to use case 3 in here. 2, I want you to calculate the efficiency for this thing. Okay, you have the plenty time. You have I give you plenty of time. You have the equations, and go ahead do a calculation. Write on the paper, take a picture, and submit through GroupMe. Okay, and ready, set, go. I give you 10 minutes for doing that. How about that?
What do you mean by verify?
Well, you have. Do you know what I mean by that equation? Which equation do you know? There's the equation to determine if it's okay to use safe case 3. Okay, I want you to see what the value is from that equation. See if it's in the satisfactory range. Again, it is actually a case 2 for this problem. Okay, you have to check that equation before you can start using case 3 equations. Okay.
We submitted on GroupMe or Moodle.
Group me. Okay, I already received 2 submissions. Good. So we started 11:34. Okay, so we'll be ended on 11:44. We have 5 more minutes.